Sorry to
No.
annoy you.
No. It's my mistake. Anyway,
Sorry
yes.
to
Now we can watch
annoy you.
the. We can watch
It's
this
my mistake.
video. Okay, then
Anyway,
I send you link. Keep that link, and later on you
sorry
can
to
see the content
annoy you.
throughout this YouTube
We can
link.
watch
This
my mistake.
video. Okay, then I send you link.
Yeah, I got it.
Post link. Okay.
Yes.
Okay,
Thank
then
you.
let's continue. Let's continue. And as you know, there are many restrictions for underwater wireless optical communication devices. All devices are incoherent. Unfortunately, we cannot use coherent modulation format and coherent detection. And we don't have high-speed external modulators. So we need to apply direct modulation only.
Okay.
And so narrowband direct intensity modulation we need to cope with because laser diode can be modulated in gigahertz, but LEDs are about 10th megahertz or 100th megahertz. And power optical intensity is not so big, but this problem might be solved by choosing a better laser diode.
Okay.
The situation is slightly changing. And at receivers, detectors have narrower electrical boundaries. It's not 1 gigahertz, but about 100 megahertz or several hundreds megahertz. And I want to demonstrate a novel narrowband modulation format based on PAM4 or PAM8 and partial response signaling.
Partial response signal. Okay.
PRS for short is partial response signaling. Later on, you can see the full spelling. Here, partial response signaling.
Okay.
Okay. And full swing LEDs should be enabled by applying this PAM4 PRS or PAM8 PRS.
Okay.
Okay. This is very important. This is my original idea and not published yet. So if you help me, you can be co-author of this paper. And this type of PAM4 PRS or PAM8 PRS can have some error correction ability at the receiver side. Maybe you don't understand why this modulation format has error correction ability. So I will explain.
Okay.
Okay. Well, first of all, what is partial response signaling? It's one of control methods for inter-symbol interference of communication signals. Okay.
Yeah.
Do you know what is the inter-symbol interference?
It's it have some noise. No, it's
It's not nice. It is because of this dispersed signal itself. Okay? So, for example, if we have a bit sequence 101 and
yeah,
we transmit the on-off keyed signal
yeah.
for this 101 sequence with a very narrow bandwidth channel, then pulses for 2 ones might be dispersed. Do you understand?
Yeah,
It can
okay.
widen. And 101 we send, but the detector may detect all one or all zero because
Okay.
of the dispersed pulses. This
Okay.
is inter-symbol interference.
I see. Uh,
Okay,
okay.
and PRS is a modulation format which allows controlled ISI inter-symbol interference. The,
Okay.
the very important part is we need to control ISI by ourselves with some aim. And here, there is an example to explaining partial response signaling. This figure shows sampled the transmission signal for one bit, just for one bit, okay?
Yeah.
And horizontal axis is for time. And this TS is symbol time. TS is the period for one symbol. The symbol
Okay.
duration is TS, okay?
Yeah. Okay.
Okay, then we use, usually we use very narrow pulse, the width is less than TS to transmit the
Okay.
signal. Basically, we need to use a narrow pulse, which pulse width is less than TS, okay?
Okay.
But in this case, we use a pulse as a basic pulse to transmit the signal, which have wider pulse width than TS.
Okay.
For example, in this case, we may use 2TS rectangular pulse, which has a pulse width of 2TS. 2TS.
Okay.
It means,
2 TS.
yeah, it means all the signals are interfered.
Yeah.
All the transmission pulses are interfered with the next pulse.
Yeah.
Okay, this is what we call the controlled ISI. By using a wider pulse, we can make some controlled ISI.
Okay.
Okay, but we need to suppress all the ISI at different the detection timing. Here it's written. For example, if we want to transmit a bit one at the time time zero, but we repeat transmit the same bit at the next symbol time TS. So we send a symbol twice. Okay,
Okay.
but we don't send any the pulse at different time instances. If we want to transmit next bit, for example, 101 case, pulse 0 at TS, then we don't send anything at TS and 2TS. And the next pulse would be sent at the time instance of 2TS. For 101 case, next pulse starts from 2TS. But as you know, we sent one twice at 0 and TS. And time 2TS, we sent another pulse again. So here we sent 1, 1, 1, 1. So for time instances TS and 2TS, it should be a smaller signal amplitude, but because of the intersymbol interference introduced by our strategy, we sent some amplitude. Anyway, it's very difficult to understand from this figure. Okay,
Yeah.
let's move on to the next one. Okay.
Okay.
So
Yeah.
if we use this pulse for bit 1 at time 0,
Yeah.
then it should have a wider pulse width like this. But this pulse does not have any amplitude. I mean, amplitude is 0 at
Okay.
another time instances like this. Okay.
Okay.
Okay. Then next we want to send pulse 1 again, bit 1 again at time instance of TS. We send this one, or we don't send anything, or like that. So this is so-called dual binary because the pulse amplitude is determined by the two consecutive pulses. Okay, if data sequence is 1, 1, then we send this wide pulses at the time 0 and the time TS. Then the summation of these two pulses are sent, and the resulting out of the pulse would be this big amplitude pulse.
Yeah.
Okay, if we send data 1, 0, and
Okay.
we assume bipolar transmission. So at time instance 0, we send pulse with positive polarity, and
Yeah.
for time instance TS, we sent a pulse with a negative polarity, and it added, and the out of the pulse would be like this.
Okay.
401 like this, and 400 like this. So as you see, you can see here, at the time instance TS, we may have 3 amplitudes. Okay,
Yeah.
if this amplitude is 1 and this amplitude is 2, 2 or 0 or 0 or minus 2.
I
Okay,
see.
by introducing this controlled ISI, if in the case we transmit binary PSK signal with this dual binary pulses, then we send 3 valued transmission signal. The I pattern is like this. Okay.
Yeah.
The merit of this method is the narrow bandwidth, because we sent same signal twice, or we use wider pulses. Then we can make narrower the transmission bandwidth. Instead, we have to use more power to transmit signals, because we need to determine this we need to send and receive these 3 leveled transmission signal.
Yeah.
Okay, it results in the more some power penalty on the BR characteristic. In this case, maybe 2.7 or 2.5 dB power penalty would be introduced. Okay, then the merit is narrowing the transmission bandwidth. In this case, we can make the bandwidth half of the basic binary PSK case, but we need more power.
I see.
Okay. As I explained, UOWC systems, the bandwidth is very, very important. All the devices are very narrow band. So, so if we want to design high-speed systems, then we need to make the signal boundaries narrower. So this is the basic idea. Okay.
Yeah.
Then how to generate this signal is shown here. Basically, we make signal in a program, eh? And I explained it, the idea with binary case. Eh? So it's called dual binary. Dual binary means PAM2 PRS. Okay, and we call it 2. Yeah? PAM2 PRS is so-called dual binary.
Yeah.
But the generation method is same for PAM4 or PAM8. Okay. For example,
Okay.
if we assume PAM4 signal as the original transmission signal, it's launched into this type of
Delay.
encoder, delay summation encoder. So, we pass through the signal, pass the signal through the low pass filter to make the bandwidth narrower. Okay, so the idea is very simple. Eh? These are diagrams for PAM4 PRS signal.
Oh.
For different different signal to noise ratios. Okay, in the dual binary case, two valued PSK signal was changed to three valued dual binary signal. But in the case of four values PAM4 signal, then PAM4 PR signal is seven valued signal. So if we transmit this signal without error, we have to consume more power. So this is why we need to consider a power penalty on the error rate characteristic.
Okay.
Okay. Very frankly, we have to keep this eye opening wider by making the transmission signal power bigger. Okay.
Okay. Wider.
We can make the boundaries very, very narrower,
I
as
see.
you can see here. Ne? We can halve the transmission boundaries. Okay.
Okay.
Then I want to compare this scheme with other schemes in UWOC transmission experimental test setup. And my junior, Professor Nakamura, is working on OFDM-based UWOC systems, as he explained yesterday, very, very simply.
Yeah.
But I think OFDM is not suitable for direct modulation, direct detection, optical communication systems. Because OFDM systems request very high linearity for laser diode and photodetectors.
Yeah.
Okay. And basically, OFDM signals should be transmit via coherent optical link, coherent communication link. But as I told you, UWOC systems cannot be implemented in coherent manner.
Okay.
So I want to focus on PAM4 or PAM8 and PAM4 based PRS or PAM8 based PRS. But the problem is the noise immunity, as shown here. As you saw here, if we want to make the signal bandwidth half by introducing this type of dual PAM4 case, dual PAM4 PRS signal, then we need to have more signal values, signal levels, It means we have to transmit more signal power.
Yeah.
And without more power, noise immunity will be degraded. It is shown here in black. Okay. So
The M is
I
sorry.
want to solve this problem. And I skip this. I skip this.
Okay, okay.
Do you know convolutional coding?
No,
Convolutional error correction coding?
no, I just know only some simple concept from Hamming
Okay,
coding,
okay,
something like
it's
that.
okay. Then I want to ask you to study convolutional coding.
Convolution coding.
Yeah, simple one is okay. Simple one is enough. But convolutional coding is the key to understand what I want to explain.
Okay.
Okay. And just wait. I may have some slides. Just wait. Not here. 救出 The slide may be in Japanese, so sorry. Not here. This one. Then I want to show you. Okay. This is the very simple configuration of convolutional coder. Here, X is a binary input, 1 or 0. Okay.
Okay.
And here we have to write some exclusive OR.
Okay. Exclusive OR.
Exclusive OR. Here, this point and this point and this point, we have to write exclusive OR. And 1 bit is converted into 2 bit. So efficiency is not good. But this convolutional coding is very strong. And it was introduced and was used in Voyager. Do you know Voyager?
No.
Saturn Explorer.
Yes.
Launched by USA, maybe 1977 or so. Saturn, do you understand? We are on Earth. We are on Earth. Okay. The next planet is Mars. Yeah? Earth, Mars, no Mars. I can't remember the name.
Could you type?
Just wait. Saturn.
1977.
Saturn. This one. Oh, no, you can see. I see. This one. Saturn.
Ah.
Saturn Explorer.
Okay.
Pattern Explorer used this convolutional coding. Yeah? Because it's very strong. Anyway, you can see two delay here.
Okay.
Yeah?
They.
Then two delays here. It means this convolutional encoder has states indicated by the content of these memories.
Okay.
Okay, for example, 00 or 01, 10, 11. So this convolutional encoder has four states: 00, 01, 10, 11.
Okay.
Okay, okay. And then if we, okay, let's start from 00. And the next input X is also 0. Then this encoder states is moved to from 00 to 00, like
I
following this
see.
arrow. Okay, but in the case of 00 and X equal 1, then it moved to 01.
Yeah.
And from 01, the encoder states moved to 11 or 10,
Yeah.
or like this. This encoder, the states change is shown, represented by this diagram.
Okay.
State transition diagram. It's called
Okay.
state transition diagram. So from 00 to 0001, or 01 to 10 or 11, or 11 to 10, or to
Zero.
11, or like this.
Okay. Okay.
And next figure is so-called trellis.
Yeah.
Trellis. Do you know?
Twice.
Trellis.
Yeah.
It's expanded in time. That this state transition diagram is expanded in time. So this is time 0, but it starts from 0. It's only one state. But next time, time 1, then the next state would be 00 again, or 01. So 00 or 01. Then next one, from 00, 00 or 01, and from 01 to 10 or 11. So this, on this trellis, the transition can be represented with this arrow. Okay?
Yeah. Okay.
And very importantly, these states are not fully connected. These states are not connected fully. So we
Yeah.
cannot move from 00 to 11 or 00 to 10. We cannot move.
Okay.
Or also from 01 to 00, from 01 to 01, we cannot move.
Okay.
This is so-called the trellis, or this state transition diagram is has limited transitions.
Okay.
Yeah? Limited transitions. So this is why we can correct errors of the convolutional coded signals. Convolutional encoded signals Y1 and Y2 are represented on this trellis, but this trellis has a very, very limited and limited or restricted transitions.
Okay.
And all the transmitted signals should be followed these arrows, limited transitions on this trellis. However, if we got error during the transmission, it cannot be follow the arrows on this trellis. In this case, this red thick dashed line shows a sequence with error.
Yeah.
Okay, so if we test the received signals on this trellis, then we can recover original transmitted sequence
Okay.
from the received sequence with errors. Okay,
Okay.
then and we can have a very very big coding gain. We call it coding gain. The the point why convolutional coding can correct errors is
Yeah.
this restricted transitions. Restricted transition limited trellis or transition limited state transition diagram. Okay, so if
Okay.
we have some state limited transition, transition limited trellis or transition limited state transition diagram, by using trellis, we can correct errors.
Okay.
And why we have this limited transition is based on correlations between outputs. I mean, in this case, y1 and y2 is calculated. They are calculated from 3 bits. Okay.
Okay.
Current input bit is, for example, called x0, and this is called x1. This is called
Yeah.
x2.
Yeah.
So these two outputs are calculated from 3 consecutive inputs.
Okay.
Then next output is calculated from newer 2 bits and another 1 bit.
Yeah.
Like that, outputs have correlations with former outputs.
I see.
Okay, okay,
Okay.
let's go back to the PRS case. Not here. PRS case. No. TRS case. We generate the signal with this encoder. It means output, 2 consecutive outputs has correlation because we send same symbol twice.
Yeah. Okay.
This means this PAM, for example, PAM4 PRS signal also has limited transitions if we make some state transition diagram, or we make a trellis for this signal. Okay.
Okay.
Okay. Then we have tried to implement very, very simple MATLAB simulation code to demonstrate the error correction ability of this scheme. And the student, Mr. Inever, needed a very long time, about 3 years, but he
Yeah.
has already demonstrated some
Okay.
amount of coding error we can have with this scheme. Not enough yet, but about 2 dB coding gain now we have. And now we are trying to enhance the
Yeah.
coding gain by changing the algorithm, error correction algorithm.
Okay.
Okay. And another topic is this one. Not another, a very related one. Which
Yeah.
one? Ah, it's with this one. This one again. And my new fourth grade student, two of them joined half a year ago
Yeah.
in my laboratory, and I trained them for half a year by teaching signal processing theory or communication theory, how to make simulation programs with MATLAB, or how to treat deep learning, or how to programming in Python, like that.
Wow. Half
Goes
year.
half a year.
Teach a lot. Wow.
They got some good results.
Wow.
And what I asked them to do is to decode. Okay, are you right?
Yeah.
Are you right? To decode this convolutional code with deep learning.
Yeah.
And they also got a good result, and much good results than Mr. Inaba's outcome. Mr. Inaba only has 2 dB gain, but new students
Yeah.
showed, but for different signals, for convolutional coded signals, they showed more than 5 dB coding gain we have by introducing deep learning to decode this convolutional coding. Okay.
Okay.
Then when you come here, I want to ask you to do experiment together with us.
Okay.
First, we just make signal by using arbitrary waveform generator, and we just detect the electrical signal with digital storage oscilloscope and get signal waveform, and decode the signal with MATLAB or Python.
Okay.
Okay. Okay. So I'm so hungry. So today,
Yeah.
let's finish.
Yeah.
Anyway, so I want to ask you to study about convolutional coding.
Yeah.
Okay.
Okay. For my homework is a convolution
Mm.
code by
Convolutional
MATLAB.
coding and bit decoding.
Bit.
Bit decoding. I write. And bit decoding. This one. Someone there? Punturi? Mino-san? No?
I stay home now. Yeah.
Hi, just wait, please.
Yeah.
I received someone from somewhere, Amazon or something. My wife's
Okay.
wife's purchase. Okay, anyway, convolutional coding and bit decoding.
Okay.
It's a popular technology, so you can easily find some documents or some books in your
Okay.
laboratory. No, library. And if
Okay.
you can't find anything, tell me. I will find something and send you. Okay?
Okay. I will try first. Thank you, Sensei.
Okay.
So I have some question about lecturer
Okay.
from Professor Honma.
Professor Homer.
Yeah,
From tomorrow, do you
yeah,
start
tomorrow.
his class?
Yes,
Okay, I need to ask him.
yeah. Oh,
Do you
thank you.
you can send the email by yourself.
Okay,
I'm Satoshi Honma S 本間 @山梨
okay, thank you. For this lecture, it is the laboratory lecture. Is it the lab or have some
No,
theory?
some lectures. Yeah,
I see.
ordinary lectures.
Ordinary lecture.
Mm. Mm.
In
I'm not
English
sure,
or Japanese?
but attendant is only you, I
I
think.
maybe have
So person to
another.
person, it's person to person class.
I see. Okay,
So you can do very easily
okay,
via online.
okay.
So
Look like I have another one to join in the class.
what
I
kind?
think
Which one? Which one?
someone join the class of
Just wait.
Professor Hanma.
My one on Monday. Uh, let's discuss later.
Okay, it's okay.
Just wait. Another one. I'm trying to find your information on our CNS. Just wait.
Okay. However, please
Huh?
have dinner. Too
I just
hungry.
go to CNS counseling phone
Yeah.
on the next week. Only 3 classes you have registered at this moment, and you have an intensive course, I think, right?
Yeah.
I'm not
Intense.
sure. Have you received any message from the lecturer of the intensive course? Not yet.
Not yet.
Not yet. Okay. Then you
From
just
uh
wait. Hmm? You have. Oh, you have. He has 3 students. So okay. Do you see my 何あれだ。
your class?
No. Do you see my screen yet now? No, not yet. Okay, maybe here. Okay. Click this link and enter log into the CNS.
Yeah. Okay. This one is yeah. I have seen this
You read?
information.
Yeah,
Yeah.
and
But
Professor Dr. Homa want to discuss with you about how to organize the
okay.
class.
Okay.
So you can write some message on the CNS.
Okay. But I at least
Here,
I should say
here,
like
here.
okay.
Uh, no, you may have some response button here. Okay. Do you have
Okay.
some button here?
Yes, I have.
Right,
Like
reply
in
button.
yeah.
Then you can write your message on CNS. It may
I
be
see.
better, I
Okay.
think. Right.
Okay. To discuss the task. Okay.
Okay. Okay. Do you have another question?
No.
No, at this moment.
Yes.
Okay. Okay. Sorry. I'm
Thank
so
you really.
sorry to late for the late starting.
It's
Okay.
okay. It's okay.
Okay,
Thank you really much.
bye now. And if you have anything you want to ask me, contact me via teams, it may be better,
Okay,
I think.
okay,
Okay.
okay, okay. Thank you, Sensei.
Okay. Then have a good night. ね。
Yeah, okay,
バ
good
イ、バイ
night.
now. Good night. おやすみなさい。